Ampere's circuital law. Let me introduce this Ampere's circuital law first. What is its significance, and what's the comparison between Biot-Savart law and this? Biot-Savart law is used for finding magnetic field induction due to different type of systems like straight conductor, circular coil at the center, circular coil at that. At the same time, Ampere's circuital law can also be used for different type of systems. Their main applications are again straight conductor, then solid cylinder outside and inside, then thereafter solenoid and toroid. These are the four applications. But this law is also for finding magnetic field induction only. Then why do we require this? Here we have some solenoid and toroid. Toroid is also an infinite solenoid wound up over a ring. Then that's the reason why we are to study Ampere's circuital law also. Let us see what's the statement, and as far as the statement is concerned, as and when I'll start explaining this Ampere's circuital law in terms of pehle statement, then suddenly Gauss's theorem will come into your mind. Why? Because Gauss's theorem, that means I want you to compare between these two, Gauss's theorem and Ampere's circuital law. What's the comparison point? Point number one is, in Gauss's theorem, we used to talk in terms of total electric flux or total surface integral of electric field, that is E dot ds. Whereas in Ampere's circuital law, we are talking in terms of total B dot dl, because there we had closed surface, here we have closed circuit, closed loop. That's why total B dot dl. But there for E dot ds, we had one term, electric flux. But here in Ampere's circuital law, we don't have any pakka term. Instead, we keep using total line integral of magnetic field. So that's why. And some more comparison points I'll mention further after this statement. Let us see. Total line integral of magnetic field for any closed loop in vacuum is mu naught times the total current threading the closed loop. Total line integral of magnetic field for any closed loop in vacuum is mu naught times the total current. So mathematically, total B dot dl is mu naught times total current, right? List of application. Number one, infinitely long conductor. There we had only conductor. Then in a special case, we used to study infinitely long, but this time as main topic, it is infinitely long conductor. Obviously, the result we would be getting same. Number two, cylinder, infinite cylinder or solid cylinder. Number three, solenoid. Number four, toroid. But before starting all these applications, I'm willing to give comparative chart, which I was trying to explain initially. Comparison. So at first, total electric flux 1 upon epsilon naught times total mu naught times total. This way, first application, infinitely long conductor. This one, due to infinitely long conductor. Similar to Gauss's theorem, we used to consider imaginary Gaussian surface. Here we will be considering for each of the application imaginary loop known as Amperian loop. This is I, this is R, this is B, this is DL. Tangential, both are tangential and shown at the same point. That's why same line. Total TL is 2 pi r, therefore B is not by 2 pi I by r. It implies that B is inversely proportional to r. So this topic appeared very much formality, very easy to interpret. Now I'm moving over to another application, infinite cylinder. Due to infinite, this time I need to draw very cautiously. This is current, right? Original radius r. This is Amperian loop. B dl, r is greater than capital R. Again, same thing, repetition of previous topic. I'll be skipping few steps. B mu naught by 2 pi I by r. B is inversely proportional to r for outside observation points. inside, that means R dash is less than capital R. Now new cylinder I am to consider at the point of observation. So now this is small R dash. So at this point only, same way inside when solid. Because for outside points it was immaterial whether it is solid or hollow. In both the situation it is same. But now in case of hollow, what will happen? For solid we need to discuss in length, but if it could have been hollow, so I need to mention I is equal to 0, therefore B is equal to 0. Now for solid, mu naught times I dash. Here it was I, but now it is I dash. Slightly reduced value. We need to show the calculation for I dash in terms of I. If cross-sectional area is pi r square, in case of cross-sectional area being pi r square, current was I, then in the situation when cross-sectional area is pi r dash square, I pi r dash square upon pi r square, pi will cancel, therefore I dash is equal to I. Coming back, mu naught times I r dash B 2 pi r dash mu naught I r dash B is mu naught I r dash upon 2 pi r square. It implies that B is directly proportional to r dash for inside. On this basis, we can show graphical variation. Also, it is directly proportional. It is on the surface. On the surface, roughly broken because on the surface it is 0 now. Hence, now what is solenoid? We need to first know what is solenoid. Insulating wires such that, and one more point, solenoid behaves magnetic dipole such that anti-clockwise phase behaves as north pole. Now we'll be understanding how. Firstly, let's have the diagram for solenoid. Now this application of amperes is very simple for us to understand. All of you must have noticed that we had been assuming or considering an imaginary loop around the system where we are willing to apply Ampere's circuital law. That imaginary loop is known as Amperian loop. So here also, like previous two applications, again we are to consider Amperian imaginary loop. Let's see how. Firstly, I'll be showing current. This way current is shown. Now Amperian loop, where small n is number of turns per unit length. Very interesting point. This is B, magnetic field along the axis of dipole. So these are magnetic field lines. That means solenoid is behaving as a magnetic dipole. Lastly, right end is behaving as north pole because right end is clearly indicative. Now you could see the current is going this way, this way, this way. That means anti-clockwise. That's why anti-clockwise end is behaving as north pole. This is clockwise. That's why left end is south pole. Diagram thing we have, therefore from equations 1, 2 and 3 we have BL is equal to mu naught NLI. L cancel, therefore B is mu naught NI, where N is number of turns per unit length and I of course current. Mu naught is 4 pi into 10 raised to minus 7 Tesla meter per ampere. Hence it is done. There is one factual knowledge that at extreme end it is roughly average. That means mu naught Ni by 2. At extreme end B dash is mu naught Ni. Here comes fourth application. Toroid is a helical system wound over a ring. That's why infinite solenoid. No well-defined north pole and south pole. How? Let's see in a diagram. And this is R. This is B. Always at any point along the tangent. Here also B is equal to mu naught Ni, where N is number of turns per unit length. such that n is n into 2 pi r, since length of solenoid is equal to 2 pi r. Here in the given scenario, length of solenoid is 2 pi r, therefore n is n upon 2 pi r. Unlike previous topic, there is slight variation in n, otherwise final formula appears the same.